Good evening, everyone. Can you hear me okay?
Good morning, and yes, good morning.
Hello. Hello.
Hi, Anne.
Are you using this? Hi, Kessera. How are you?
Yeah, great.
Oops,
Yeah.
you're muted.
Can you hear me?
I still can't hear you.
Yep, I can hear.
Yeah. Mm.
Volume up.
And can you hear us?
Now I can. I couldn't before.
Okay.
Okay.
So if you were talking to me, I'm sorry I didn't hear anything.
All right.
So Kessa, are you hoping to have some time at the end today?
Yes. Yes.
And how much time would you like?
I think just maybe 5 to 10 minutes, and maybe
Okay.
so that they can I like to discuss with them about about what we like to continue the sessions in the consultative meetings. Right? Yeah.
Okay, sounds good.
Yeah.
Morning, everybody.
Well, it's their evening.
Oh, good evening, everybody. It's good morning for me. Morning.
Morning to you and evening, everyone.
Sorry, what? So I put the PowerPoint into the shared document, but I made a couple updates this morning. And so I will put the new one in later, just two simple things.
Mhm.
Everyone's a little blurry and I don't know if I'm just tired or these glasses just don't work on a computer. That's much better.
Much better.
Not very fashionable, but function over over
But
beauty.
the fashion, they back and forth, big glasses now,
Mhm.
very
Right.
fashionable.
I have students who wear glasses who don't need it, they just think they're cool.
Yeah, so you can look into your old eyeglasses and it worked fine now.
Back when we were kids, it was a curse if you had to wear glasses. Did you get teased? Wearing
No.
glasses? I never wore them. Bill
For
said
me-
he got teased, he would just beat everybody up if they teased him.
I didn't wear glasses until I think I wear for the long distance glasses.
Hmm.
Yeah, when I studied my PhD, that was when I read a lot. And then my eyesight become farsight. Mm.
So I assume we'll wait a couple minutes and see if more people come on.
Yeah, I think we wait until 7:05. How about
Okay.
that? Yeah, and then we can start.
I'm gonna heat up my tea. I'll be right back.
Okay. Burin, you think can we start?
Yeah, I think we can. Yes,
Okay. Yeah.
they'll
Okay.
come later.
Okay.
Well,
Let's-
hi, everyone. You want to start, Kessler, or do you want me to jump in?
Yeah. Today at the end of the session, 10 to 15 minutes before the session ends, I would like to discuss with the team about the next session that we are going to have with Dr. Ann, that what would be the expectation from the project with the team members, that we are going to move to the next level of the sessions. So yeah, I think let's enjoy hearing from Dr. Ann first, and then we discuss later. Okay. Yeah, please, the floor is yours, Dan.
Thank you. Hi, everyone. Thank you for attending. And I just want to start it out to see if anyone has questions from the beginning. Okay, so what I'm going to plan to do today is to continue going through the water quality test, but not as methodically, because you can read the unit, you have the link to the unit, but to highlight some more in terms of some of the practices. Sam, question?
Yeah, good morning and good afternoon. I'm Sam from Cambodia.
Hi, Sam.
Yeah, I have one question regarding to some material that we applies with the water qualities. And for those schools and in the other countries, maybe it's not really challenges, but in Cambodia we do have challenges with the material that we use to for applying in water qualities and teachings in secondary school as well as the high school in Cambodia. So regarding to the some material that we are lacking out, so what's the other alternatives or other choices can be used instead of those? Thank you.
So you're talking specifically about materials or lack of materials?
Yeah.
So for the pH, pH paper can work really well. And that's pretty, is that accessible to you?
Yes. For pH papers as well in Cambodia, yes.
And temperature, they can use thermometers. You're gonna see with the next test for dissolved solids. I'm not sure about that. Joe, do you know? I know that there are probes. But if you don't have probes because they're dissolved, I mean, there are also kits that can be purchased. But then, you know, that's other materials that would be needed in terms of everyday materials to measure dissolved solids. That may or may not be an option for you. So there's 5 water quality tests in total that I'm talking about. And there may be some that just aren't feasible for some countries based on materials. But there should at least be 3, the pH, the temperature, and the turbidity, that are can be done with more everyday materials.
But you could, for dissolved solids, you could also just try to take some water, filter out any of the large particles, right? Like you don't want little pieces of dirt or little pieces of little leaves in there. So you could filter out any kind of suspended particles,
Mhm.
and then you could just let the water evaporate.
Right, or boil it off.
Boil off the water and just see the residue, right? So that might be one thing, just to get the kids to realize that there are dissolved things inside the water that could influence the quality of it.
Yeah, and students are so amazed when you boil off water and you see stuff, because even though we would think that they would know, even like salt water, to have that visual, to see salt left over in a container is really surprising to them. So yes, so that's another idea. For dissolved oxygen, that's a little more challenging. But again, so you may end up picking and choosing based on the materials that you have available to you. And then you'll get some other ideas today, like for a turbidity test. Does that answer your question, Sam?
Yeah, thank you very much. Yes. Okay, thank you.
Any other questions? Okay, so it does feel like there's limited time, so I guess I'm going to apologize in advance. I'm not going to try to rush, but we won't necessarily be jumping in and out of breakout rooms. So please make sure that you ask questions, or if you have comments or suggestions as we go, kind of just jump in. Okay. So last we met, we were talking about the test for thermal pollution, and in every student reader, so how I approach it, I have students read the reader first, and then when we're trying to then talk about the science ideas, I never have to lecture. So I avoid lecturing. What I do is, since they've read the materials, then I can pull the ideas from them, and then we look at the causes and we look at the consequences. So I'm just going to read this carefully, because we are going to look at some assessment items later, and these are going to be important ideas for students to be using. So thermal pollution is a really different kind of pollutant because it's hot water, and that can happen for 4 reasons. So hot surfaces, and for some of you, you know, depending on your climate, it can be warm all year. For us, we'll never have hot surfaces in the fall when we do this water quality test. The surfaces heat up, and when it rains, that rain gets hot. You may have seen, like in the hot summer, when it rains, it looks like steam, right? Cutting down trees near waterways because they provide shade. Factories take in water to cool their machinery, and if they can dump it right back, they thermally pollute the water. And then during construction, or if people cut down trees and there's a lot of erosion, that dirt can get in the water through runoff. And those particles, and not just dirt particles, but other particles can absorb heat. And then there are 4 consequences, right? So if the water's too hot, fish are going to die because they only live in certain temperature ranges. Warm water promotes algae growth, and warm water can't hold as much oxygen as cold. Algae, how many of you are familiar with algae? Right, so it's a little green plant. It's a huge problem in places in the United States, not necessarily only from thermal pollution, but also it's one of the consequences of too many dissolved solids, such as nitrogen and phosphorus, like from fertilizer, and that's going to be from a different water quality test. Okay, so this is also at the end of the student reader for temperature, and students are presented with a picture and asked. So the first question, at point A, the temperature is 11.8 degrees Celsius, and at point B, it's 12.8 Celsius. So like, what can you say about the water quality at point B based on the temperature test, and how do you know, and what might be the reason for it? And then there's a second question here that's looking between point B and point C. And then students practice, and we do this together so that they get a sense before we go out to the stream that we're really comparing temperature at 2 different locations and subtracting, and then those temperature differences is what we're going to use to decide if there's thermal pollution or not. So here's the question again, and for the first one, students would simply subtract and get a 1 degree temperature change. And according to the standards, that would mean there's no thermal pollution and there's excellent water quality. And if they look at the picture between A and B, this is going to be their qualitative data. They can see that there's really no causes of thermal pollution, and that there's trees that are providing a lot of shade. And in addition, those tree roots hold soil, so there's no loose soil. So it's trying to get students to be able to be good observers, look for causes. In this case, try to explain using the picture and using other information they get, in this case, quantitative data, to figure out if there's thermal pollution or not. And for the second question, they would subtract again, and they would get an 8 degree temperature change. That would mean there is thermal pollution. I would provide them with the standards. It's fair water quality according to temperature. And then they would explain that we can see factories between location B and C, and there's pipes, and factories take in the cool water. They cool their machinery. They dump another hot water back in, and so we get this abnormal temperature increase. And then in terms of action steps, permeable roads. So this is right in the city that I live. I went around and I took some pictures, and you know, I point out to where in the city this is. Some students are familiar with the neighborhood. Construction fences. So this is right down the road from our school. They're building some homes nearby. And so I want to point out, as students drive to school, take a look at these. You know, what do you think they're for, right? They're going to help capture particles so they don't go into waterways. This is the part of my own school that has a green roof. And we talk about green roofs and how those can help. And then for factories, we talk about that factories can have retention ponds or holding ponds that they can put the hot water in and let it cool. Then they can reuse that water, or they can then put it into streams. And then just planting grass whenever there's loose soil. So some of these students can do themselves or their families, and some of them are beyond them, but they get a sense in terms of there are actionable things that we can do to help prevent thermal pollution. Now this allows me to go back to this diagram. So the research clearly shows that learning occurs over time with multiple exposures, right? We can't just expose students to some idea once. So we can go back to this diagram, and now we can understand thermal pollution. There's lots of potential possibilities of thermal pollution in this diagram, right? So we get to revisit point source and non-point source pollution, again, build their understanding over time. If students collect data and they write an explanation, so this is the rubric that I would use. I would want them to define the test when they introduce it and then make a temperature claim. And then I would want them to say, you know, there is or is no thermal pollution and explain what that is. I would want them to report quantitative evidence at locations A, B, and C, and then explain that if the tests are positive or negative, and then tie in the consequences, but not only say the science idea that, oh, if there's thermal pollution, fish are going to die, but to connect it to their stream. Did they see any dead fish? To say it's positive because it can promote an algal bloom, and to say we did not see algae at our section, or we have algae, but it's not because of thermal pollution, et cetera, et cetera. I want them to talk about the weather and surfaces, because we have plenty of surfaces in our neighborhood, but why, with all the surfaces, and if it did rain, how come there's no thermal pollution? So tie this idea, it's November, it's Michigan in the United States, so it's cold. So we do have the potential for thermal pollution. If we went out in the summertime and we did some measuring, we might find very different results. And then again, prediction action steps. I believe Joe went through a generic rubric for assessing explanations. So this could be modified, or this could be used as part of that rubric. So I want to share with you, this is an actual 7th grade student part of their temperature explanation. And I want to emphasize 2 things. One is the importance of feedback. These are challenging tasks for middle schoolers. They haven't been having these experiences before, so they do need a lot of support. So this student reported results, which indicated no thermal pollution, and then wrote stream section 5 is positive. It means no thermal pollution and is healthy and all organisms could survive. So that's a really nice claim. They actually reported their evidence first and then made the claim. So when we think of claim evidence and reasoning, it's not necessarily just linear. But then if you can see in the yellow, this student continues and very nicely shares and articulates all the causes of thermal pollution. But what this student didn't do was actually use those science ideas to explain the data and then why that data counts as evidence. So again, for these, I give electronic feedback because I have terrible penmanship. Teachers can certainly give handwritten feedback, but this person says that there are 4 causes of thermal pollution in warm weather, man-made surfaces heat up, et cetera, et cetera. And I say on the right here, okay, great science ideas. Now talk about it. There are many surfaces around our stream, and it did rain earlier, so why isn't there thermal pollution? So I provided some prompts for that student. This student also talks about there's, factories taking in water. So again, I say, great science idea. So now discuss it with our stream. Can we rule this out? and wide becomes the rebuttal. Same thing here, erosion, so, and particles heat up. And I say, great, now talk about it. Do you have particles? If you don't, why aren't they heating up? So, whoops, so I'm constantly trying to get them to actually not just talk about science ideas, but I want them to use their knowledge and connect it to the data. So this is the revision that the same student made. In the yellow is the original ideas, and then in the blue, now the student has come back and has made more connections to the actual stream. So talking about surfaces on the top, and then this wouldn't affect our stream because the weather has been cold. Talking about factories do not affect our stream because there aren't any, et cetera, et cetera. So this importance of feedback, especially early, right? So in terms of scaffolding student learning, at the beginning explanations, I do provide a lot of feedback. Sometimes I will put the rubric up on the projector and have students take a look at their own explanations and take notes and then revise it, because we know, teachers can have large classes, and giving individual feedback is challenging, but it's extremely important. But then students can give each other feedback, or we can use, like I said, a rubric with students. Okay, so in terms of assessment, we've talked about scientific explanations. It's a really nice tool to students to see not only as a teacher where students are, but for students to see where they're at with their understanding right now. But I'm going to show you an assessment task that is a similar idea in terms of trying to assess student understanding. Remember earlier, we said the conversation is changing, that we're no longer just exploring science topics, but we want students to make sense of phenomena, right? So not just what do you know, but what do we want students to be able to do? And we want them to figure out, we want them to be able to explain, we want them to solve problems. So if we're going to adjust our curriculum, we really want students to build understanding over time. We want them not just to use the science ideas, but we want them to engage in the science practices and cross-cutting concepts. So it also means that we have to not only change the conversation during the curriculum, but we have to do so with our assessments as well. If our assessments don't align with our instruction, then there's a problem. So our assessments have to change as well. So in the old way, if we were just exploring science topics, so back when I was a beginning teacher, I might have some version of this on like a traditional test. I might ask students, what is thermal pollution? And what are the 4 causes of thermal pollution? And make sure you explain each one. And what are the 4 consequences? This is actually easier for students because lots of students view science or learning in general as memorizing a bunch of stuff, spitting it back on a test, right? What's more challenging is the new way where we want them to make sense of phenomena. So this is the new kind of question that aligns with the instruction. It's a little bit cramped in here because I wanted to put the whole question on the screen. But if we see on the top right here, it says use the picture, the standards and causes and consequences related to each water quality test in the questions below to help you answer. So here we have, and this should look familiar because it was a similar thing at the end of the student reader, but they have a picture that they have to analyze. This question is about between point A and B. So the temperature of point A is 6 degrees. B, a mile down, is 13 degrees Celsius. And based on temperature as a measure of water quality, what conclusions could you make about the water quality at B? How did you arrive at this? Show all of your work. They've already done this. And so they're now being assessed on it. That's the first part. And the second part, what is the reason? Now they're going to use the cause for these results and explain the cause thoroughly and also the consequence, and to use only the picture. So some students want to write down everything they know. They want to write down every cause, every consequence. But what I'm trying to get them to do is to actually look at what could really happen out in society, and figure out and analyze and then synthesize what's going on, and then one action step. So a response would look like this. We have a 7-degree temperature difference. That means there is thermal pollution and a fair water quality standard. The cause of thermal pollution is a dirt pile from construction. It's raining and the dirt is being carried to the river. So you can see in the top of the picture, there's a big cloud with rain. The dirt in the water absorbs the heat, causing thermal pollution, and the consequences, algal bloom, because warm water promotes algae, and it's in the picture. In this case, one action step during construction fences should be put around the area so that they can capture any soil and prevent it from getting into the river. Now, it looks kind of like a simple task, but this kind of thinking is very challenging to students, mainly because they're not used to these. They're used to answering science questions just with science ideas. They could do that, but this is a real transition into getting them to actually use their understanding with some data that they've been provided with. Here's an actual student response from this question. So we have the same picture. So this student here, this student here, the water quality point B is fair. And she put the standard because the temperature difference is 7 degrees Celsius change. And that means there's thermal pollution. And then she's articulated the cause for these results is soil erosion, and then particles like dirt from construction, getting into the water, making it darker so it absorbs heat, and the consequences in algal bloom, et cetera, et cetera. And then she has this idea about putting up retention fences. So here's the second part from B to C, right? So we have a temperature difference of 13. To expect a poor water quality because there's a 12-degree temperature difference. The cause this time is hot surfaces, many houses with rooftops, et cetera, et cetera. It's raining, right? The water's hitting the roof. These are storm drains. And this is actually a picture of 4 storm drains that are right on the street next to our school. And it's at the low part. So students have actually seen these before. And so they talk about a consequence of fish dying if the water gets too hot. And then an action step, there's lots of different things. A green roof could help because it won't heat up. Rain gardens or holding ponds that allow time for water to cool. And then again, we get an actual student response. So I'll give you a minute to look at that. Oops, sorry. So I've broken this into 3 different questions, A, B, and C. I could put all of them together. You know, there are multiple steps in terms of student reading ability. What I have found is lower level readers benefit greatly if I break it into 3 steps, at least until they get some practice in terms of these types of questions. For higher level learners, I could have practice questions that are broken apart and then put all together. You just have to see in terms of, you know, the population of students. Like every teacher, I have a range of students. And so I have found that this format helps students.
And I have a question.
Mhm.
Yeah, why did you give this point, 3 points, 4 point, 2 point for the consideration? Because the action step, I think, even it is only one action step, but it is important to have their action.
So I agree, and that would just be a teacher decision. But conceptually, those are not as challenging as some of the science ideas. And so I think there's just more detail needed to explain the causes and consequence. Really what it is there's 2 points for the cause and 2 points for the consequence and 2 points for the action step. I just kind of put them together. And for some students, they end up answering the entire question in this space. And then they get to this question and they go, oh, I already answered that. So I really treat the entire question as one. I tell the students I'll read it. But yeah, that would be a teacher decision in terms of emphasizing the action step more.
Okay. Yes, thank you.
Any other questions? Okay, so in terms of all the water quality tests, they really all have the same format. We investigate what is the water quality measure. So why are we testing for it? If you think back, the second lesson, students go online and they take just a 10-minute look at how experts determine water quality, and we get this list and they say, oh yeah, experts look for pH and temperature and dissolved oxygen. We don't even know what most of those are, but we're just trying to see what they do. And so we want to figure out, and we use those student readers to get familiar with the water quality tests. What are the causes and the consequences? Are there action steps that we as individuals can take? I always want students to make predictions. I want them to collect and analyze data. And then I want them to develop artifacts. Scientific explanations is a large part of this curriculum. Scientific models. So in your next session with Joe, he's going to introduce you to Sage Modeler, which is a computer modeling program, which is just perfect for water quality. So he's going to introduce that to you. Is that tomorrow?
Wednesday.
On Wednesday, and you'll be creating water models. And then these assessment tasks. And then there are other things that, other types of artifacts, I'm going to show you one in a minute, that can help students learn and show their understanding. But in developing any artifact, my goal is that in the process of developing the artifact, students actually learn. So it's not only like an assessment of what they know, but in the process, it will get them thinking more, helping them make more connections, helping them develop deeper understanding. I also want that artifact to make student learning visible. And not just to me as the teacher, but I want it visible to the students. I want the students, as they're creating artifacts, to reflect. I want them to think about, oh, this idea, these concepts and these relationships, I really understand these. And these ones I'm a little shaky on. I have questions about, and I need to learn more about. I also want the development of artifacts to create a culture of learning. I want us together as a team, teacher and students, to understand that science is a real collaboration. And I do have individual things as well, like the last tasks I was showing you, but that in science, though, this culture, our classroom environment is one of investigating, learning, developing understanding. And then I also want sometimes opportunities to share with the greater community. I want my students to understand that science isn't just in our classroom and with our unit, but that we do connect to the greater world. So we're looking at the water quality of a stream right at our school, but we want to extend those learning ideas to our community, to our state, and globally. I want them to view themselves as global eco-citizens. So the next water quality test is conductivity. And I'm not going to go step by step through it because it's in the unit. Like I said, they're all pretty similar in terms of the format. And then as the students understand the format as well, that they get this pattern and then they can really dive into the ideas. So those substances we tested for pH. We also test again for conductivity. We have a probe that measures the amount of dissolved solids. There are probes that measure nitrogen and phosphorus. We don't have the resources to have those probes. And as Joe suggested too, if you don't have the resources, they could filter out or boil off the liquids of some of these. But we're focused in for salt, nitrates, and phosphates, or nitrogen and phosphorus at the 7th grade level or middle school level. We use nitrogen and nitrates kind of interchangeably and tell them they'll learn more in high school chemistry. But we retest those, and it allows us also to talk about concentration because they put huge amounts of the substance in the water. And so when they test, they'll get outrageously high numbers. They won't predict what those high numbers, but we retest those. And then one thing I want to show is every time we do a water quality test, we always share all the results. So we have 6 classes of 7th grade. So A, B, C, D, these are the 6 classes on the left. And then at the top is just a quick picture of our stream and the different sections. And then students always write their data because we want to see across each class, like A period, for example, if we have similarities or differences. We also want to look at all the classes and see if there are any outliers. So in the middle right here, you see that where the 2 stars are, these numbers are vastly different than everyone else's numbers. And so the option was, and both of these teams used the same probe. They shared the probe. So it looked to be, so kids also help to understand that there's error in science, and we have to take a look at human error, instrumental error, or legitimate results that might be outliers and why they might be outliers. So both these groups went out and retested and got similar numbers as everyone else. You may not have that luxury. The body of water might be far away, but it does open up this idea of the importance of multiple tests to verify. And so every water quality test we do, we always share all the results. Okay, so I want to show you another example of an artifact. And this is an artifact students made for conductivity. As we're looking at this, I'd like you to keep in mind 2 questions. One on the right here, do these types of artifacts help assist students in developing deep knowledge? And do they make student understanding visible? They made these artifacts in teams. So they work together. So I'm just going to pop out and then show you this, and then we'll take a look. And in the process, we'll learn about conductivity. Yeah, let me know if I'm going too fast. Okay, so what I'm going to do is they had a lot of fun making these, and I have found through the years that one thing that we have to stress is there should be science ideas, and it shouldn't just look pretty, because some students will want to spend all their time making it look pretty, but they don't have any substance. So they have pretty strict criteria to just, work with the science ideas and then make it look pretty at the end if there's time. But there's no criteria for it to look pretty. Visuals have to enhance. It can't be silly, but this is this group, and so their question is, are there too many solids in our stream? And they first define what is conductivity. So they explain, and they give us some background. So the causes and the consequences. And so they're going through what would be kind of similar to an explanation. At least it has the components of it in there. They share their predictions, and for this year, so what I did is I had groups get the data from all, use the data on the board from all the groups, and then talk with groups about their predictions. So they were creating a presentation based on the class's prediction and the class's results. So when you see the sections here on the left, so these are the various sections where data was collected, and these are the numbers. Now, over 400 milligrams per liter is poor, you'll see here. And for their data, everyone got around 1,500 milligrams per liter, except this section right here, this last one. And this is a pond, and it's connected through a storm drain with our parking lot. And it's always higher. The water goes from the pond and dribbles into the stream. Okay. And then they share some qualitative evidence, and this isn't standing alone. The students are presenting this. And so, we want our students not to only become strong written communicators, we also want them to become strong oral communicators, right? Because communicating is such an important skill, no matter what our students decide to do as adults. And so they're explaining these as they go. And then this is actually, they created, this is our stream. That section that was really high is this pond here. And they put a pipe here to show that there's a pipe that connects to parking lots. And then in section 1, they've also put a pipe here. Section 1 has storm drains that are connected to condominiums that are also right next to our stream. And then they say, okay, you may be asking, why are nitrogen and phosphorus consequential? And then they step by step go through a death cycle. So they start talking about if we have excess nitrogen, I'm going to share this part. So they start talking about excess nitrogen. They connect it to beautiful, look at it snowing. Sorry, we have getting snow. Excess nitrogen and phosphorus that comes from fertilizers from these beautiful lawns that are right next to our school. And then they step by step go through a death cycle where excess nitrates and phosphates can cause algae. And then we have all this excess algae, which is food for fish. Oops. And then that excess algae is going to die and become, it becomes excess food. So we have this excess organic waste. That's more food for bacteria, and the bacteria population really explodes. So we have excess bacteria, and all that excess bacteria uses up oxygen. And so there's not enough oxygen for fish. So they really carefully talked us through that. And then they came up with a conclusion about high conductivity, and they have some action steps, how to prevent high conductivity. So be more mindful of the amount of salt we lay, because, this was at a time where it had snowed, and then using less fertilizer. And then they cited their sources. So that's one group. And because I want us to, again, think beyond just our school. We have given presentations to our, on the other side of our stream, we have a retirement home. And the retirement home and the condominiums in Green Hills are in this, my school is in a small watershed, and all of our actions impact the stream. So we have taken a group of students over to that retirement home and given them a presentation. And so various groups have presented their findings in these PowerPoints. So let's get some feedback. What do you think of that type of artifact? If we go back to our questions, does it show that students have, does it illustrate student learning? Any comments? So the question was, do they assist students in developing deep knowledge, and do they make student understanding visible? What do you think? Any feedback on this PowerPoint or Google Slides? It can be either.
Yes, based on what I have already learned from your presentation, the students, yeah, they like to do the deep knowledge, I think, and because that's too more theoretical, they have to cite many things to report their their thinking, their found. Maybe it is better to give more hands-on, and then they know what is nitrate, phosphate. For the middle school, I think it is hard based on our experience here. That's the opinion from me.
So yeah, it's middle school. It is hard, but they can do an understanding, and when they use this, they teach each other as well, right? And so it reinforces the ideas.
Yeah.
So there's in the chat, the artifacts help developing deep knowledge, linking what they have seen from actual experiments and explained phenomena by using scientific knowledge. Yeah. So they find this particularly engaging, and that artifact was only created in a couple of days. So they were able to create that in a fairly short amount of time, working as a team, and then presenting it to the class. And then some went to present it to the retirement home. Okay, so I'm going to continue then.
And may I ask the questions?
Yes.
Yeah. So I just want to know, how did you group the student?
Oh, that's a good question. So I think, so in terms of grouping students for the water quality partners, the part that they're going to, when they adopt a stream, usually I let students pick their own partners, unless I know there are people who can't work together, because of course friends are going to want to pick each other. They're going to spend a lot of time together. So if I can see that they choose each other and they can work, that's better. Otherwise, I try to group students who I think will bring the best out in each other or help weaker students. You know, so sometimes it's interesting because in science, sometimes weaker students can actually also be the more creative students, and they can come up with ideas that really impress everyone. So oftentimes weaker students just lack confidence and experiences, when it comes to the PowerPoint, I grouped people from different groups so that they would, because they had different results, so that they would come in and that they could actually share their results. So if there were 3 to 4 people in a group, it wasn't from every single group, but there would be, they would see different parts of the stream. They would bring in their different ideas. So the grouping, you know, can be one of the more challenging things for teachers. But so, yeah, I try to bring a variety of students together when it comes to these kinds of artifacts. And then sometimes when it comes to water quality groups, I might end up putting 3, you know, a couple of weaker students together so that, because I can provide that group with a lot more support where other groups can kind of be off on their own. But mixed groups are, to me, like the best thing. I already answered that. Okay. Okay. So the next test is dissolved oxygen. And I think what I'm going to do is, we have a dissolved oxygen kit. If there's time, I can show you a student artifact like I just did. But what I'd like to do is I would like to give you some data here. This is actual data from our stream a few years ago. And the sub-question for this is there enough oxygen to support aquatic animals in the stream? And so they got location A, B, and C, 110%, 79%, and 94. These are, according to standards, the first 2 would be good water quality, and the third is excellent. It had recently rained, and there were dead cattails, but high stream flow. And then in terms of excellent and good, that if it's excellent and good, that means the water will support life. So there's enough oxygen. And if it's fair or poor, there's problems that there isn't enough oxygen. And I don't know if you can see, it got really light here. Flowing water captures oxygen, and organic waste causes oxygen depletion. I don't know why that's so dark. So I would ask to write an explanation that a scientist might write that answers the question, is there enough oxygen to support aquatic animals in the stream? And I'm just wondering, in terms of time, if instead, not have them write one, but evaluate students.
I'd have them, I think they would, why don't you ask them, we'll take it further.
Okay, so question to you, would you like to individually write an explanation? And then we'll take a look at those, or do you want me just to show you a student example and we'll evaluate that one? What's more beneficial to you?
I think student examples.
Okay.
Yeah, thank you.
Okay, so this is an actual 7th grade example. So I'll give you a minute to look at that.
Is it in individual student works or groups?
This was done individually by a student.
Okay.
Actually, students first shared and talked with each other, and then they individually wrote it up. So this is a technique I like to use. I like students to first share in small groups their ideas, and they can jot notes. But then I'd like to individually have them write it up, because that allows me to check for individual students instead of like one student ends up writing it and someone else doesn't really understand. So yeah, this was after students had talked, and then he individually wrote this. Mhm. Does anyone need more time in terms of reading it? Okay, so if we're thinking about the explanation framework and the various components, someone want to share one component that you see that Jeffrey has written in his explanation? You can just jump right in. What do you notice about this claim? What's one thing?
So the claim, the first sentence is the claim, and
First sentence.
first sentence is claim.
So does everyone agree? And what do we think about that claim? Would you consider it to be a strong claim or a weaker claim?
Enough.
So if we want a claim to show accurate relationships between variables, I see the variable of dissolved oxygen. I see a connection to aquatic animals, and I see a standard. So there's 3 variables in here. So some students at first, they will say it was good. That will be their claim. I get this all the time. It was good. And I have to say, first of all, what is it? And good, and what do you mean, right? So this does have a very complete claim. The dissolved oxygen level is good enough for most aquatic animals in the excellent and good range. Okay. Is there evidence that is reported?
Yes,
Yes.
from the data, 110%. And
So
yeah.
he records both at A, B, and C, gives the quantitative. In part of the explanation, is there also qualitative observations? So it's been raining
Mhm.
lately,
Yeah.
dead cattails. Okay.
Yeah.
That one.
Qualitative.
So stream flow, right? So
Mhm.
there's observations in there. And then the reasoning part, does Jeffrey explain why dead cattails or stream flow, why those count as evidence? So we would see here in red, that's a nice claim. There's some good evidence reported in terms of the quantitative. And then mixed in with the purple, the reasoning is more quantitative. So overall, how would you mark this explanation? Would you say it was kind of high, medium, or low?
I.
I would agree. This is a strong example of an explanation. Okay. And so that was the dissolved oxygen one.
Mhm.
The last water quality test that we do, but there are other water quality tests. But the last one we do is looking at turbidity, which is the amount of floating particles. And we really want low turbidity. So
And before we continue, I have a question.
yes.
Yeah. Did the student learn this knowledge before about the turbidity, about the dissolved oxygen, or they just jump to the experiment?
So what I do is I try to give students the least amount of ideas that they can do before they experiment. But no, before they went out, we read the student reader for dissolved oxygen. We talked about what it measures. And then also in this case, it's positive. So we want a lot of oxygen. Up until this point, with pH and temperature and dissolved solids, those things are bad, right? And so I want students to realize that actually not everything we're measuring is a problem. We want to measure oxygen. So we do background first, because if they just go out and collect data and they don't have
Yeah.
then it's like playing, right? And so all of this is very engaging and fun. Students love it. But I stress, we can't just play. We have to be, everything we're doing, it's going to help us develop understanding of important ideas. So, so we would talk about like, where does the oxygen come from, so that they know what to look for when they go outside. And then also the consequences, what happens if there's not enough oxygen, and then also what causes dissolved oxygen levels to decrease. So what I think I'll do is I'll show you a student example of the oxygen. I think I have up here. No, maybe I don't. So yeah, so they become familiar before we go out. And
Mhm.
again, it's like, I don't lecture, they will read first
Mhm.
and then we'll connect as much as we can. And then, yes, they go out, they know what to look for. It helps them start thinking about why oxygen might be lower. So one thing that lowers oxygen levels is if bacteria use up all the oxygen. We learned about that with the conductivity, so they can connect, right? So that they can look for organic waste. So they have a data sheet that is very targeted on what they should look for, and then what they're going to analyze. And I'm going to pull up the data sheet for dissolved oxygen.
Yeah. Okay.
Okay. So this is this is a version of a data sheet. There's a different one in the unit, but I can put all my data sheets in the shared folder. But they would record the weather. That's really important for dissolved oxygen. And then when they go out, they're going to really look for stream flow and living plants, because these are the things that can help oxygen levels. Then they're also going to look for any dead things. We have to take temperature because temperature influences. And then the kit that we use, they need to convert it. But yeah, what are they looking for? And then this is going to help them analyze their data. Okay, so. Okay, so the last water quality test that we do is for turbidity. There are several types of equipment for turbidity, and one is the Secchi disc. I don't know if you're familiar with it. So I have one, but we have a problem. We can't use this because our stream isn't deep enough. So you put it in the water, you take a look, and there are standards for, how low it can be where you can see it clearly, right? If you can only see it clearly from 0 to 2 inches, the water quality for turbidity is very poor, too many floating particles, and then it goes. But our stream isn't deep enough, and let alone we're not going to go out in a boat anyway. There's something that a high school teacher in Australia invented. He took this little Secchi disc and put it in the bottom of a tube. So he created this turbidity tube where kids take buckets and they get a sample and they pour it in the turbidity tube. And there's a little release valve here, and they look through the top and see until they can see that the disc is clear. And then they measure the distance. We have one of these that we got from our local watershed, but it's just not enough, right? So we can't use the equipment that is at our disposal. We just don't have enough. There's also equipment where you take a little sample and you put it in a box and put a light through it, and you see how much light comes out at the end. We also don't have that. So instead of saying we can't do this test, because it's actually a very crucial test. So turbidity is the amount of floating particles. When we measure conductivity, that's the amount of dissolved particles. And so in terms of any solids, these two water quality tests will give us insight into both of them. And so, and also in our area, turbidity is a problem in our community for our waterways, particularly after a rain event. So it's something I really wanted to test, and it also connects with many of the other water quality tests. So what we do is a design challenge. I want students to figure out, how can we collect the data? We're going to need 3 samples, A, B, and C. And it allows, again, time to revisit experimental design. So in pH, remember, students design that experiment. And so again, for deeper learning, students need multiple exposures. So we can ask, like, what variables should we be thinking about? Also, what needs to be controlled? So if we want to go to the stream and get 3 samples, what can we do in class that is going to help us get insight into turbidity? So we have to think about what's feasible, right? They can't come up with crazy ideas that it's impossible for us to do. We need to use everyday materials that might be found right in the classroom. We have to think about how long it's going to take. So it has to be something that can be done fairly quickly, and then anything else, right? And so what I would like to do is put you in breakout rooms just for a couple of minutes. And I want you to see if you can come up with, like, what could middle schoolers do with everyday materials to try to figure out how many floating particles are in their various sections. And so can we get in breakout rooms just for like 10 minutes, just jot down some notes on your ideas, and then I'm going to show you some common ideas that students come up with. Can we get into breakout rooms?
Yes, yes. Okay.
Wonderful. Okay. So I'm going to give you 10 minutes, come up with some ideas, and then we're just going to share, and then I'll show you some student ideas. And it is, so at 8:20, we'll come back. So are you creating breakout rooms? During,
Yeah, I made 4 breakout rooms.
okay, great.
But we haven't found yet here, Dr. Burit, to choose.
Oh, really?
Yes,
Mm.
there is no
Oh, sorry. I forgot to press open. Sorry. Okay, it should work now. Sorry.
Yeah.
Okay, we'll give everyone a minute to get here. Here it comes. Okay, hopefully you had some good conversation. So I want to do a turbidity test. I don't have any equipment. What are some ideas? Anyone want to share what your group came up with? Any brave souls? What? And this is also, so, you know, science is very risk-taking. And so one thing to try to assist your teachers in promoting this culture of learning where we take risks. We decide later on that maybe we were not going down the right path, but that we can feel comfortable in sharing ideas, and that when we share ideas, people will give feedback and we'll get other ideas that'll be better. So somehow if we really need to create this classroom culture where we're willing to throw out ideas that other people can think about and that we can think about in order to do science. So anyone willing to share?
Hopefully they are not boring with us. And
Yeah.
yes, I'm in the group 3 together with Dr. Murni, Mr. Cucu, and also Mr. Muhammad. Could we share our idea? And
Yes,
yes,
please.
first of all, we got the idea that we want to have these 3 sample of water from the riverside, near the construction, middle the construction, and far from the construction site. And then the student design 3 glass, the same glasses, plastic glass that they can, the transparent glass. We just take from any kind of image on Google, but this is not ideal because we should consider the variable. We should maintain the same size of the glass, but we pretend that this is the plastic glass that they can find at school or at home. And then the sample of the location site, we have 3 points near the construction site, middle, and far. And then we have to control also the variable that they have the same volume or the same height between those 3. And then student draw the picture about picture dog or face or something, and then put under the glass, which so all of the student will observe the order of the turbidity level from the worst until what we call it that yeah, from the first, the second, and the third. So that's show the quality of the water from the highest turbidity till the lowest turbidity. That's the 10 minutes that we discuss in group 3. Thank you very much.
So thank you. Is there any feedback to this group or questions to this group? Okay. Any other group?
I just want to add the explanation of our group. I belong to the Nurma group also.
Yeah.
So if we have 3 students in one group, so 3 students will make a measurement. I mean, we'll see the pictures under the each glass. So we have 3 reviewers or 3 what is it? 3 observer.
Yeah.
So because first we think that we only can rely on one students to observe, but then we think that maybe they have problem with the eyes, so we have to see from three opinions. So that's why if one group consists of 3 students, then 3 students have to see each of the classes.
Right, so this, 'cause I thought you said no. So this then also helps to get more consistency, right? When every student, and then it also engages every student as well. And then any other feedback for that group? Okay, is there another group that would like to share? So this is a process that I do often in my classes. I have small groups come up with ideas. I have every group share. And I say, we're looking to see if we have some overlap, if we have some consistency, or to see if this group has this great idea that we might want to all do, or if we can take that idea and make it better, or if there's some things that just aren't feasible and why they might be an issue. And so to work to come some consistent, because we want not only like the 3 members of the group doing it, but we want to be able to share the data. And if we're going to share, then we all need to do similar things. So I'm going to share with you some of the more common ideas I would get from students. Let me see if I can. Okay, so this was the challenge. And so on the left side here, this is one of the more common one, and it's similar. So the group who shared said getting 3 cups, A, B, and C. And then this idea that we need to get the same amount of water. We can't have a sample of 1/4 of a cup and a full cup. But then we could do that visual test, right? So this is a common one, right? Just do a visual test and compare all 3.
Yeah.
Or we can pour them through coffee filters. I'm sorry, go ahead.
No,
Okay.
sorry.
So this is a really common one, and these are common materials that we have. If we pour through the coffee filter, and then we take the coffee filter off, and we lay it down on the desk or on a small whiteboard, then we can visually see and compare at the bottom here, right? High, medium, low, or none. And those would match up with excellent, good, fair, and poor, because we have 4 levels of water quality standards. Now, is it as accurate as a probe? No, but you get a visual and students can really see differences in the amount of turbidity. And then another idea that groups came up with on the right here, they called the smiley face turbidity sheet, where they created, on the far right, you see poor is a dark smiley face, and then it progressively gets lighter as you go to the left, and excellent is very light. And they would literally put their 3 samples on top of the smiley face and move to see where you could see it clearly. If there's a lot of dirt or other particles floating, then you probably can't see the smiley face unless it's really dark, like in the pour. If it's very clear, then you can see it all the way to excellent. So those are 2 student ideas. Excuse me. The more common one that we tend to use are the tennis cans with the coffee filters. Any questions or comments about these? So it's a fairly simple design challenge, but it actually works. And it really does match up with the more sophisticated equipment. In terms of what happens, it's just not as sophisticated. So I could show you more artifacts. But I think what I want to do to make sure we have time and that Kesra has time, I have a conductivity, dissolved oxygen, and turbidity assessment that I'll show you in just a minute. But I want to make sure that in terms of ending the unit, well, first of all, after we do the water quality tests, I use the modeling program as a way for students to look at all their data together. So they create a model, which you'll do with Joe on Wednesday, and that helps them see the connections between all the tests, because we've done each test separately, and then, but some of them are really connected, and you can't have excellent water quality for pH and poor water quality for oxygen and make a claim that the water quality of the stream is excellent. So this idea of students having to think about a claim for each water quality test, but then an overall claim for the health of the stream. So in lesson 11, what students are doing is trying to answer that big driving question. Is our stream healthy for freshwater organisms, and how do our actions on land impact it? And there are several options. So one option in terms of scientific explanations is to have students construct an explanation and address the driving question by looking at all the water quality measures. So they would have written like a mini explanation for each of the water quality tests, and then they would come together and they would then decide about an overall claim. But that's pretty sophisticated. That's a lot of writing. Another option is to have students put in groups or individually, and they just write about one water quality test. So again, it can be done as a group or individual students, and then you would have something called a water quality summit or a symposium where students would share their explanations either individually or as groups, and then they would work to build consensus to make one claim, an overall claim based on all the evidence gathered in terms of the health of the stream. So maybe they have 3 water quality measures that are excellent, one that's good, and one that's poor. And so they basically argue using science ideas to decide then and try to create consensus on an overall claim. Okay, so that's another option. So, and then I think there's a couple other options in the curriculum too, at least maybe one other. One thing though that can really help them with this is to create that model. So in the model Joe's going to show you to use, students can actually create a dynamic model, and they can set each of the parameters to the actual results that they got. And then the model, if they've created it accurately, should help them with that claim. If they set it up excellent, good, fair, or poor, and they set every water quality test to what they got, then that will help them. So this could be done after a model, or it could be done before a model, and then they can create the model to see if it does match up, and then it will help them in terms of trying to figure out that claim. So for my PhD dissertation, I analyzed students' explanations across time, and one very unanticipated outcome, it was not even a question I was asking for my PhD, was about students adjusting claims based on new evidence. So once students made an initial claim for pH, so many students were unable to let go of that claim when new evidence came in, so that they didn't adjust their claim. Partly, I think, because they never have had those experiences. But if we think about our everyday life, here in the United States, politically, it's a disaster, but all over the world, right, there are challenges. And one thing that students don't know how to do is change their minds, and adults don't either. So during COVID, when there was some science saying, here's what's happening, and here's what we should do, people started following that. But when new evidence was gathered and the medical experts were making changes to protocols and what we should do, lots of people in the United States were saying, oh, scientists don't know what they're talking about because they keep changing things. Instead of realizing that as new evidence is coming in, we need to make adjustments, right? And so I found this in my water unit, that students didn't know how to look at new evidence that would say, oh, I need to rethink what I'm thinking right now because I have additional information that I didn't have before. And so this is one of the big challenges that I find in my unit, that I'm now helping students with as we go, to rethink their claims, to see if their claims really are supported by not just one piece of evidence, but for all the evidence. So that might be something when you're working with your teachers to let them know in terms of thinking in advance about that idea. Any questions? Or any comments? Okay, so I could show additional assessments, or Kesra, I can hand it over to you.
I think you can show more about the assessment. That would be great. Yeah.
So this is an assessment task that I use after we're done with dissolved oxygen, turbidity, and conductivity. And it's a similar format to the one we saw for temperature. I really want my students to use their understanding in a new situation. And so I have a question here, this first one on the right with the dairy farm. It's related to floating particles. So they need to realize that this one's about turbidity, and it asks what we can say about the water quality, again, the reasons or the causes, and then the consequences and an action step. The second question is large amounts of algae are seen, and they get a conductivity reading that's 880 milligrams per liter, which is really poor. And what's going on, again, the causes and the consequences. And they can see here that they have algae. Algae is a consequence of too many nitrates and phosphates, as well as thermal pollution, but this one isn't about thermal pollution. And all this organic waste from cow manure, so that's a pile of cow manure. And so if you know, in the unit, I would have students look up how much poop does an average cow produce in one day, and then how many cows are in an average dairy farm, or in other cattle farms. And then they see there's an enormous amount of cow manure, and that cow manure has to have somewhere to go or some way to dispose of it or use it in a way that's not going to damage water quality. And as bacteria break this down, it releases nitrates and phosphates, so we get algal blooms. So these are things that are happening in our community here, and some of these are bigger than what students can actually do. That's why, but they can actually come up with action steps. And then the third one is about between C and D, And this one is about oxygen. And we see up here, there's dead fish between A and B, but there's actually living happy fish between C and D. And this third question is about dissolved oxygen. 95% is very positive. And then how did that happen? So it's just another example of assessments that align with the unit, where kids aren't just writing down the science ideas, but they're actually using their knowledge in ways to show that they have deep understanding, or in ways that show me in terms of what they know right now and what else I need to do to help them develop understanding. So that's just another assessment for the unit. And then I won't show this to you now, but we give exams at our school. At the end of the semester, our students have an hour-and-a-half exam. And so my exam is a big picture with lots of stuff going on. It's got 5 graphs, all the data, the same graphs, the same data that we've collected all year, but it's a new situation. So it's a new river. And they're answering the question for the community, is what we're doing in Green City impacting our river in negative ways. And so students write a new explanation based on new data and the new picture. So they're transferring their knowledge to a new situation, but they've been prepared in smaller ways throughout the semester. So if any of you are interested in that, as we're going through the next couple of weeks, I'm very happy to share that, and I can also put that into the shared folder. Questions or comments?
You in the assessment, students have to use the standard pH bar and also DO standard. So
I'm
students,
sorry.
were the student able to
So you broke up. Could you start again? I didn't hear all of that.
Just
Yeah,
make your video off.
I have the problem with my internet connection. I'm sorry. So in the assessment, did you show the students the DO standard, PS standard, because or they have to memorize?
No,
the,
I give them the standards, but I don't give them the if it's excellent, good, fair, or poor. So when they take the the semester exam, I give them all the standards, and then they need to know, like, do we want high or low oxygen? The high one would be excellent and the low one would be poor. Do we want high, medium, or low pH? Do we want high, medium, or low temperature differences? So they don't need to memorize any standards. In a regular assessment, like the one I just showed you, I would have a couple multiple choice questions that the standards are there. And I might say, what would be the best for a stream? And then I give the 4 numbers, and then they would have to know, but they don't need to memorize the standards. Things that they can easily look up. Those are provided. Okay. Well, thank you, everyone. And I look forward to working with you over the next few weeks. I'm going to pass it to Kessera, and feel free to email me or let me know if there's other materials you'd like me to put into the shared folder, and I'm happy to do that.
Yes, thank you. Thank you, Anne. So, yeah, I like to discuss with the teams that how you would like to structure the next sessions that we are having Anne to help provide us the input, right? So if you, I can share with you
that we are having, right? So we plan to have more, right? And then we have 12, and then I think jump to the I think more 19, right? So we earlier I thought that let me stop, right? So I thought that the way that the team will benefit from her time is that now we have learned a lot from her about the structure of the units, the learning activities, and how kids conduct the activities, and how the student work are assessed, right? Looking at the sample of the students, right? But I believe that in each country context, you might not, you have different contexts, right? And the teachers that are not evenly capable of conducting the learning activities as we saw by how Anne's conduct the activities, right? So I think that the professional development activities that we should design will vary and maybe different a lot, right? So I think that the way that we might benefit from Anne's input is that if the team can start designing that how the professional development should look like, how we can help our teachers to understand the driving questions, the concept in the units, and about how to introduce this learning unit to their students. So what needs to be done if our target groups are teachers? And you might also think about what is their background. Do they have enough conceptual understandings of the units that we are introducing, or do you need to introduce any basic concept beforehand, right? So and as we mentioned some times ago, that I would like to see that how the team working together cross country, that you can plan together, and you might have scenarios that that how the teachers that who are your target group would be, right? And decide something that you think teachers will the mainstream teachers, not the top or the cream teachers, but for the for the general teachers that you think they are they can benefit from this PD, and that PD activity you can decide together, and then after that you might have something add-on that you think will be quite relevant to your context.
I lost Kesra.
Yeah, what do you think? Yeah.
I can't hear Kesra.
Mm, yeah. And yeah, how you would like to work together as a working team. That earlier when you met in Bangkok, right, you divide the team into the according to the units, right? The water quality, the interactions, and also health group, right? So do you want to remain the working pattern, the group in that first, and then maybe use the session that Anne will come for the consultation session to provide you with the input? Yeah, how would you like to utilize her time, and also be able to work with your team as well? Yeah, I want to hear your thoughts about this, please.
Dr. Mani, Dr.
Yeah.
Pacheli. Yeah, please. Yeah.
Yeah, so we actually had discussed with our team in my university, in Universitas 11 Maret, and we learned the lesson plan that Anne have sent us in the first meeting in Bangkok. And when we read all the unit lesson, we think that some part of the lesson could be applied in Indonesia, but currently we try to introduce the unit lesson to our students because we are in the Faculty of Teacher Training and Education, and now we have a STEM course.
Oh, okay.
So yeah, STEM education course. I lesson to my students, and I think when we want to train our teachers, we first want to do with our students. I mean, with our teacher students, because we have some teacher candidates, pre-service teachers training, and I think that's one way to have what kind of adjustment that we have to do if we want to implement the water quality unit lesson, and then make some adjustment also in Indonesia.
Yes,
So we think
yeah.
that we would like implement to our teachers, junior high school teachers.
Yeah.
Yeah.
Okay. So yeah, you.
So that's our plan. Yeah, but we also, there are 3 universities from Indonesia will join this project. We think to also discuss with other person in charge in other 2 universities, because actually we would like to have the same unit lesson in Indonesia implemented in Indonesia. And just so can share research, making comparison between Thai and also Indonesia practices. Yeah.
Yeah. So yeah, your target group would be the novice teachers, right? That you are under your supervision, right?
Yeah. So my STEM class is about 12 students currently, but Nurma also has STEM courses in her department. So in our first discussion, we think to apply these water quality unit lessons. I mean, discussing the unit lesson to our teacher students first. Now, for teachers, junior high school teachers.
Okay. Yeah. Thank you. And how about you, AD, or how about Dr. Pacheri from Chulalongkorn? What is your thought?
Yeah, I think the context at the Chulalongkorn University is quite similar to Indonesia. I mean, UNS. At Chulalongkorn, we have the STEM courses for pre-service teacher. But I am afraid that maybe next semester that the course will start at January 8 might not be in time to implement the water quality unit. Yeah, because the lecturers we all plan for the teaching for the next semester. Okay, and then I have talked to Moni that we are agree to has done the comparative research of the implementation, the water unit. Yeah, but we haven't talked about the detail yet because I thought that we have like many aspects that we can like write to publish anything. Yeah, but when I looking at the activity itself is may higher than the middle school student in Thailand. Like for example, like test nitrogen, phosphorus, or conductivity. So, but I will try to make the activity or the process like a fit to the middle school student. So it will, yeah. Okay. I think everything is possible. Yeah. So right now we are talking about the probe because at a couple days ago that I asked like how to measure the pH. So I go back and then we have thought the pH paper so may not like exactly, and then it will get the student like a very good number of the what they get. So I think that if the Simeo STEM Ed like provide more budget or the so to buy like a science in
Instrument, right?
instrument, yes, it will be good. Yeah, and then, so
Okay.
okay,
Yeah.
that is
Yeah, thank you, Dr. Pacheli. Yeah. So, yeah, I think maybe what we can do is that maybe we can have another like maybe meeting before we meet with Dr. Ann, right? About together among all the STEP project teams, and maybe we should revisit about the PD plan, because the PD plan that we expect it will not happen until I think March next year, from March next year onwards. So we can the team, all the three teams can think about that who will be the target groups, and how we can yes, the trade-off of this unit, do you think it will be only for the novice teachers, or will there be any in-service teachers that you have been working with in your school network? Would you like to introduce the units to them so that you can have both the in-service and pre-service target groups? So I think this can also be discussed. For example, the MOE CRT in Indonesia also has expressed their interest to learn or benefit from this program too. So I think maybe as a big group, the country can discuss about who do you think can benefit from this program, and how each group would like to decide the professional development that fit in, and also within your capacity as well. Okay. Yeah, we can set up another meeting with another teams as well. What do you think? Yeah, because this group is mainly for the faculty who oversee the water quality, right? And we still have some time to discuss about this, right? And then we can discuss as a big group and decide together, that how you would like the target group, who would be your target groups, right? As a program in each country, because based on last time we start talking about that, right? And then I think you can finalize them together, and each country might have different target group according to the focus and the capacity as well. Mm.
So I apologize, but I have to drive to my school.
Okay, yeah, thank you so much,
You're welcome.
Dr. Ann.
I
So
also-
I will send you messages about.
I also
yeah,
want to stress, I just want to stress to everyone, and Joe's leaving, that all the materials are modifiable. So anything that's been sent to you, you can change, adjust, right, do anything you want with that. And I will put more of the handouts and things that I have into that shared folder. Okay.
Yeah.
Thank you, everyone.
Thank
Bye,
you.
everybody.
Thank you.
Bye. Thank you.
Thank you, Anne.
Bye bye.
Yeah.
Thank you.
Yeah. So, yeah, I think, yeah. Do you agree, Dr. Green, that maybe we will have another meeting
Yep.
to discuss more on this and
Yeah.
how you would like, how you expect to see the result, right? I believe that it would be amazing to see how students benefit from this unit, right? And the explanation that we can help them to develop, and even the data that we can share across different countries about the water quality in their own neighborhoods. I think it would be fun, right? If students can see other countries' water quality that they also study in the same lessons, right? And I believe that what we see in and student work is very inspiring, but I know that the context will be different in terms of the foundation of how students are introduced to explanation, but we can start from somewhere. And yeah, so and Dr. Burin can set up another meeting later, and we will let you know that when it would be. Okay. Yeah.
Yep.
Okay.
It's
So,
very interesting.
yeah. But I thank you everyone for your time. I know that it's a big contribution that you spare your evening time throughout the past few weeks, and I appreciate it. But I also hope that it's beneficial to you, and hope that it will be more the how we set up this project and working together will be more fruitful for your faculty, for your university, and for your schools, communities. Okay, so until next time.
Yes.
Bye. Thank you.
Yeah.
Bye-bye. Thank you.
Good
Thank
night.
you. Until next time.
Wednesday.
Yeah, Wednesday with Dr. Joe. Okay. Bye.
Bye.
Bye. Have a good night.
Thank you.
Yeah, bye bye.
Good
Have a
night.
good night.